Hello everyone and welcome back to another mini concept, this time on pH, pOH, and titration curves. So when we came from the last video, we talked about acids and bases and how to classify them and what make them Arrhenius, Bronsted-Lowry, or Lewis bases. This time we're going to be talking about what we use numerically to describe these acids and bases. Acids and bases, they dissociate into different things. Of course, depending on the type of acid and base, it will donate either an H plus ion, a hydroxide ion, or it can donate an electron pair. But bottom line is, there's always an exchange, there's always an imbalance, right? Now, when there isn't an imbalance, that's when we reach neutrality, and we're gonna talk about that in a bit. So perhaps for those of you already in, well, this is a Gen Chem 2 topic, so I assume you guys have already heard about what pH is, right? So we have the pH scale. pH scale goes from 0 to 14, where 0, the closer you are to 0, is the more acidic, and the closer you are to 14, the more basic it is, right? So when we're more basic, like I put up here, when we're more basic, it's basically saying that we have a lot more of our we have a lot more OH in the water, right? We have a lot more OH in the water, and this is because this is probably because we have more base than acid in our solution. Now, on the other hand, if we're more acidic, then that means we have more acid in our solution, right? It's that simple. Now, how do we know if there's going to be an imbalance or not? Well, that's if it's any number that isn't 7, right? So if the pH is if pH less than 7, we are acidic, right? And if the pH is greater than 7, we are basic. Now, if it's exactly equal to 7, we are neutral. An example of neutral solution is water, or an example of a basic solution is sodium hydroxide, and an example of an acidic solution is hydrochloric acid. Now, when it comes to acids and bases, they also have a strength to them, right? So I'm gonna put this down here, up here rather. Okay, I'm gonna make it a bit smaller. Now, acids and bases have a strength to them. An acid is considered strong. Hold on, let's use red. So, acids are considered strong when its pH is from 0 to 2. Now, weak acids are anywhere in between, right? So pH is equal to 2.1 ranging to 6.9. Now, how about for bases? Hold on, let's make this a clear dash. Okay, there. Now, how about for bases? For bases, so we have strong base. A strong base would have a pH of 14 to 12, or we can do it the opposite way, 12 to 14. And a weak base would be a pH of 7.1 to 11.9. So that's how we determine it based on pH. We can also recognize strong acids and strong bases and weak acids and weak bases based on the chemical formula. So for strong acids, hold on, let's move this down here a bit. Actually, let's remove this. There. Okay. So for strong acids, they are typically, hold on, these are halogens. Halogens plus a hydrogen, right? And this can be, for example, HBr, HCl, right? And that's these are examples of strong acids. An exception to this is HF, hydrofluoric acid. That's a weak acid. Right there. Now, for weak acids, it's given by organic acids such as acetic acid. So if it's organic or it has a COOH group, OOH, that's called carboxylic acid. If it has an organic group, then that's a weak acid. Also, if it has more than one hydrogen. So if it's polyprotic. Now for strong bases, they're typically when you have group 1 or group 2 metals. So we have the alkali and alkali earth metals. Alkali and alkali earth metals. Metals plus OH. So what's an example of this? Let's just move this one. An example of this is NaOH or KOH. Now for weak bases, it's for any other metal as well as amines. So other metals or nitrogenous compounds or amines here, like this, like ammonia, and then you have an OH group attached to it. So that's how we determine them based on formulas. Of course, it helps if you're lucky in your exams. They might tell you that it's a weak acid or a weak base, or a strong acid and a strong base. Well, it helps to know. It helps to know the difference. Alright, so now let's get to the solving. Right? So solving for pH. Solving for pH and pOH, we actually have quite a few formulas. However, they're not all that hard. So we have the first one. So pH is equal to 14 minus the pOH. pOH, or rather, let's start from the very beginning. pH plus pOH is equal to 14. Right? Now, if you want the pH, it's 14 minus the pOH, and pOH is equal to 14 minus the pH. Right? So that's pretty straightforward. This is just the most basic formula for pH. So let's say let's say that the pH of a certain solution is 6.1. What is the pOH? Well, all we have to do here is just 14 minus 6.1, and that would give us 7.9. So our answer is 7.9. Right? And that's how you use that formula. It's really quite simple. Now, how do we make it more complicated? Because, well, as it stands right now, this is really, again, quite simple. Well, pH can further be written down like this. So this is our, let's just call this the pH given formulas. So when they give you the pH or the pOH and you need to solve for the other, you tend to go for that one. Now, how about when you don't have the pH or the pOH yet and you're given concentration? Well, now you can derive for pH using this formula. So pH is also equal to the negative log, this is common log, of the H plus ions, or the negative log of the concentration of the acid. pOH is equal to the negative log of the hydroxide ions, and this is also equal to the negative log of the base, of the concentration of the base. So let's say that concentration is given and you need to solve for pH. this formula will allow you to get the pH simply from the concentration. And you can actually substitute this and put it into the other formula so that you can solve for the pOH and the pH. Right? So this is the concentration derivation. Why is it not? Okay, there. We're gonna call this the concentration derived formulas. And that's actually it. These are our two sets of formulas for solving pH and pOH. So let's try this. So let's say that we have the reaction of, let's say we have an HCl solution. We have an HCl solution with pH. Hold on. With pH. pH being, well, HCl is a strong acid, so let's say that it's 1.2, right? The pH is 1.2. What is the concentration of HCl? So since we're looking for the concentration, we need to use the concentration derived formulas, right? Now, how do we reverse engineer this? So we can go back, we can go here. So pH is equal to the negative log of the acid, the concentration of the acid, which in this case would be HCl. So we can also say that this is equal to 1.2. Now, recall what this means. The answer to this is 10 to the power of negative something, right? The negative log, which here is actually our pH. 10 to the power of negative pH. So in order to solve for HCl, we just have to substitute here our pH. So it's 10 to the power of negative 1.2, and that will get us an answer of 10 to the power of 1.2, 0.06309, which for significant figures, the concentration of HCl would be equal to 0.063 molar. There. And again, how do we get this? It's because if we convert this into exponential form, we get this version of our equation. And that's how you reverse engineer our equation here. Now, how about if I want to get the concentration of OH? Let's say that we had HCl react with NaOH. Well, we can do the same thing, but this time we have to subtract first our pH. So how would that look like? So let's say that the reaction was HCl. Let's change our pen. HCl plus NaOH. This dissociates into, or not dissociates, but rather it forms H2O and NaCl, or sodium chloride. So here we know that the pH of HCl, or the pH of the resulting solution, is 1.2, right? The pH of the resulting solution is 1.2. So we need to solve for the concentration of NaOH. Now, NaOH is our base, right? And since we know that the concentration of the base is given by our formula here, we can reverse engineer it by solving for the pOH. So pOH first is given by 14 minus 1.2. So 14 minus 1.2 is equal to 12.8. So our pOH is 12.8. Now 12.8 will be equal to the negative log of our base, which is NaOH. Converting this again into our converting this into our exponential version, we just have to raise 10 to the power of our negative pOH. That's 10 to the power of 12.8 negative. And that gives us concentration of, that is 1.6 times 10 to the power of negative 13 molar. And that's it. That's how you'd solve for the concentration of our base given this data. Alright, so now let's move on with titration curves. Alright, so I hope this part is clear. Titration curves allow us to plot the changes in pH. Now, how does that work? Okay, so this is used during, well, obviously, titration. And titration, hold on, we're gonna shrink this, and we're gonna shrink this as well. Okay, so titration is, well, if I'll try to draw it. Let's see if I can make it understandable, because I'm not the best at art. But basically, titration is when you have, let's say, this beaker of substance here. You have this beaker, and you have an acid inside. For example, you have an acid, and you want to test with a burette there. You want to drip out base, right? You want to neutralize the acid inside. So this one has base. You want to slowly drip inside the acid a certain amount of base so that you can reach an equivalence point. And I'll describe that later during the titration curve discussion. But basically, when you do titration, you want to find the concentration of a certain substance. And you do that by adding another substance in slowly. And in titration, normally the way we figure out that, oh, okay, so they're now at pH 7, oh, they're now at a certain pH, is by adding an indicator. But that's not part of this video. Instead, we're just going to be talking about how titration curves work when you actually do titration. So titration can happen between four different combinations. So you can have strong acid plus strong base. You can have strong acid plus weak base. You can have a weak acid plus strong base, or you can have a weak acid and a weak base. Now, what makes these combinations different from one another? Well, I'm about to show you right now. So, okay, here. Oops. Okay, so for a strong acid and a strong base, right, we describe the strong acid's pH. This is pH, and this is amount of base added. Okay. So let's say we're given a certain strong acid. This is 2. This is 1. Let's say this is pH 1. This is pH 14. So if we have a strong acid and a strong base, and we're starting with an acid, right? So our curve will start here. Now at a certain point, let's say that we had 25 ml, okay? Let's say that we had 25 ml of strong acid. At a certain point, near that 25 ml, this is 25 ml right here, there's going to be a sharp turn upward. And since it's going to slowly turn into a strong base, it's going to level out to the point where it's going to approach the strong base pH. Now, what's the logic behind this? In a strong acid and strong base titration, strong acids and strong bases, they reach an equivalence point that looks like a straight line. Okay, this is not a straight line, but basically, that's when they reach pH 7. Right? The pH at the equivalence point is 7. And an equivalence point is when there is equal parts acid. So acid, equal parts acid and equal parts base. There. And it will look like this. It's a sharp turn because, well, the influence of a strong base would be strong. And that means that it would be a sharp influence, right? And the influence of the strong base would make it so that it would have a higher ending pH. Because it needs to level out with the identity of the strong base that we add. It gets easier the more we illustrate the other types of titration curves. Let's try this time with a strong acid and a weak base. So a strong acid and a weak base, let's just copy this. Okay, so we're gonna put this down here. Oops. Put this down here, right there. Okay, now we're just gonna remove everything else. Okay, there. So for a strong acid and a weak base, we know that a weak base is anywhere in between, well, not, and anywhere below 12 and above 7, right? So we have a strong acid. We start at the same spot. And we still have that sharp turn here at the towards the middle. However, this time it's like a soft curve. Right? Let's say that this right here is it's like 11.9. And my drawing is not very accurate, but basically pH here is like 11. Let's say pH here is at 11. The equivalence point right here, the equivalence point at a strong acid and weak base titration would be slightly below 7. Like slightly below 7. Why is that? Because, well, the shift would be the shift would be a lot earlier. All right, so now let's move on with titration curves. All right, so I hope this part is clear. Titration curves allow us to plot the changes in pH. Now, how does that work? Okay, so this is used during, well, obviously, titration. And titration, hold on, we're gonna shrink this, and we're gonna shrink this as well. Okay, so titration is, well, I'll try to draw it. Let's see if I can make it understandable, because I'm not the best at art. But basically, titration is when you have, let's say, this beaker of substance here. You have this beaker, and you have an acid inside. For example, you have an acid, and you want to test with a burette there. You want to drip out base, right? You want to neutralize the acid inside. So this one has base. You want to slowly drip inside the acid a certain amount of base so that you can reach an equivalence point. And I'll describe that later during the titration curve discussion. But basically, when you do titration, you want to find the concentration of a certain substance. And you do that by adding another substance in slowly. And in titration, normally the way we figure out that, oh, okay, so they're now at pH 7, oh, they're now at a certain pH, is by adding an indicator. But that's not part of this video. Instead, we're just going to be talking about how titration curves work when you actually do titration. So titration can happen between four different combinations. So you can have strong acid plus strong base. You can have strong acid plus weak base. You can have a weak acid plus strong base, or you can have a weak acid and a weak base. Now, what makes these combinations different from one another? Well, I'm about to show you right now. So, okay, here. Oops. Okay, so for a strong acid and a strong base, right? We describe the strong acid's pH. This is pH, and this is amount of base added. Okay. So let's say we're given a certain strong acid. This is 2 let's say this is pH 1, this is pH 14. So if we have a strong acid and a strong base, and we're starting with an acid, right? So our curve will start here. Now, at a certain point, let's say that we had 25 ml, okay? Let's say that we had 25 ml of strong acid. At a certain point, near that 25 ml, this is 25 ml right here, there's going to be a sharp turn upward. And since it's going to slowly turn into a strong base, it's going to level out to the point where it's going to approach the strong base pH. Now, what's the logic behind this? In a strong acid and strong base titration, strong acids and strong bases, they reach an equivalence point that looks like a straight line. Okay, this is not a straight line, but basically, that's when they reach pH 7. Right? The pH at the equivalence point is 7. And an equivalence point is when there is equal parts acid. So acid, equal parts acid and equal parts base. Right there. And it will look like this. It's a sharp turn because, well, the influence of a strong base would be strong, and that means that it would be a sharp influence, right? And the influence of the strong base would make it so that it would have a higher ending pH, because it needs to level out with the identity of the strong base that we add. It gets easier the more we illustrate the other types of titration curves. Let's try this time with a strong acid and a weak base. So a strong acid and a weak base, let's just copy this. Okay, so we're gonna put this down here. Oops. This down here, right there. Okay, now we're just gonna remove everything else. Hold on. Okay, there. So for a strong acid and a weak base, we know that a weak base is anywhere in between, well, not, and anywhere below 12 and above 7, right? So we have a strong acid. We start at the same spot. And we still have that sharp turn here at the towards the middle. However, this time it's like a soft curve. Right? Let's say that this right here is it's like 11.9. And my drawing is not very accurate, but basically pH here is like 11. Let's say pH here is at 11. The equivalence point right here, the equivalence point at a strong acid and weak base titration would be slightly below 7. Like slightly below 7. Why is that? Because, well, the shift would be a lot earlier. It's gonna be a lot earlier because it would still be primarily acidic as the weak base is there. The weak base cannot completely change it to make it like equilibrate in a sense at 7, because it's weak compared to the strong acid. So that's why it's just going to have a pH at the equivalence point that's slightly less than 7. Now how about a weak acid and strong base? So now a weak acid and strong base would look the same. However, this time it's reversed. The roles are reversed, right? So hold on, let's just remove this. This time we have a weak acid. We don't start at 1. We will start at, like, let's say 3. An example of a weak acid would be acetic acid, and this is 14. Alright, so here, if we have a weak acid and we we have 25 ml of it and we have a strong base, we expect the shift to be before 25 ml because you don't need to add so much, right? But this time the shift wouldn't be a sharp shift, it would be like really smooth. And then at the top it's sharp. There. It's like you see the difference here. There's like it's like kind of smooth there, but then here it's like it's abrupt. Now, the equivalence point at a weak acid and strong base titration here at the equivalence point would be slightly greater than 7. And the end point would obviously be like around 12 to 14. Now, this is what the titration curve would look like for a weak acid and a strong base. Now, lastly, for a weak acid and weak base, well, this one's just it's kind of self-explanatory. I guess you guys can guess. It's gonna look soft curve on both sides, and it will end at a lesser than 12 pH. So again, this is at 3, this is at 14, so it will be soft, and then it will be soft as well here. So it's like playing around the middle there, and this would be pH 12. So here the pH would be the pH here would be much closer to 7, because just like the strong acid and strong base, they equalize, and weak acid and weak base, they equalize as well. It just so happens that oh, this should be a bit shifted to the right, sorry. So this should be like, just imagine that like there, yep, right there. Okay, there. Sorry, pardon the drawing, but they basically equalize, and it would be close to 7, like there, approximately 7. Now, how do we compute for the pH and pOH of certain solutions that we titrate or analyze given titration data? Okay, now this one has another set of formulas. So here are the curves side by side if you guys want to compare. This is the strong acid and strong base, strong acid and strong base, strong acid and weak base, weak acid and strong base. Hopefully you guys can see the difference here. The curve is really what you want to look out for. It's not just about what number the curve will end on. It's also about like how the curve is laid out, because the curve will tell you which one is strong and which one is weak as well. Alright, so in titration there are questions that would look like this. Hold on. Let me bring this down here. I'll duplicate this. Allow me to paste the sample question. Alright. Oops. We don't want that all in red. So hold on. Oh no, we're lagging now. Alright. There. So this is an example of a titration curve question, right? And we want to plot the points on our titration curve. First though, we have to identify what are our acids and our bases here. So this is actually the example that we've already been doing for like a lot of our acid and base examples. We have hydrochloric acid reacts with sodium hydroxide to form water and sodium chloride. Now we have our titration curve. Our titration curve would probably look like this. We recognize that this is a strong acid, this is a strong base, so we just draw our curve here, there and there, and it should look like that. That's what it should look like. It's a moderately sharp curve. There. That's what it should look like. Now we'll label those points later. Shrink this so that we can. Alright, so this is what we have right now. how do we solve for the initial pH of the acid, the the pH when we add the zero point 0.1 liters of hydroxide, 0.12 and 0.15? Well, we have another set of equations, and they're actually quite easy to derive. So let's say that we don't know the concentration of our HCl, right? Because our HCl at a certain point, it will change its molarity, its initial molarity at the beginning, right? So HCl initial is 0.1 molar, and the volume initially is 0.15 liters. Right. Now we want to get, for A, we want to get the initial pH, right? So how do we get the pH again? We get the pH by getting the negative logarithm of the concentration of acid, which is HCl. This is equal to negative log, that's lag, log of 0.1 molar. This is equal to 1. So our pH at the beginning is equal to 1. So that means here we start at pH. Now for number 2, our new formula is going to look like this. So before the equivalence point, we want to get the concentration of our analyte, right? Of our analyte. Analyte. The analyte is what we're trying to analyze, not the one that we're dripping in, right? So since we're analyzing HCl, we know that that's what we want to get. The concentration of the analyte before the equivalence point is going to be equal to the excuse me, the molarity of the analyte times the volume of the analyte minus molarity of the titrant and the volume of the titrant over the total volume. There. So total volume is pretty straightforward, right? I'm gonna move this up. We're gonna run out of space. Alright, there. So for this one, what is the reason why we use this formula? Well, just a quick overview on why we use it. MV is actually equal to the number of moles of substance that we have, right? And how do we get that? Well, M is equal to mole over volume, and if we adjust that, we get MV is equal to mole. So what are we doing here? We're trying to subtract the amount of moles of our, this is the moles of analyte, right? So moles of analyte by the moles of our titrant. Moles of our titrant. Because here we know for a fact that we have more acid than we do base. And that's how we're gonna figure out what the concentration of our acid is, given that we're adding more base, more volume to our solution. Right? So that's just some added understanding to why we use this formula. So now we're gonna substitute, right? We're gonna substitute and we're gonna put here our, hold on, let's do it here on this side. We're gonna have our molarity, which is 0.1 times 0.15 liters. This is for our analyte. I'm gonna move to the right. And then we're gonna have minus our 0.125 molar. And how much did we add? According to the question, we added 0.1 liters. Alright, now our total volume would be 0.1 liters plus 0.15 liters, which would give us a total volume of, hold on, total volume of 0.25. Now doing the calculations, on the top you would get 0.0, hold on, let me double check. You would get 0.0025 over 0.25. So 0.0025 divided by 0.25 is equal to 0.01. And this is our moles. This is our molar concentration for our HCl currently, right? Now what do we do with the molar concentration now of HCl? Now we can get the pH, because the pH is going to be equal to the negative log of 0.01, and this is equal to 2. So the pH at when 0.1 liters of NaOH is added is equal to 2. Now, how do we approach part C? Okay, let's move this here. Let's have more space. So part C, same process, right? Same process. Also, this is like the point right before we reach the equilibrium point. So it's like right here. This is let's say that this is already pH 2. pH equals 2. There. It's not the scale, but that's basically it. How to plot it. Now, for letter C, let's give this a shot. Now, we'll do the same formula. We'll just do 0.1 m times 0.15 minus 0.125 m times 0.12 liters over 0.27. Now, if you do the calculation, you'll actually come to find that this is equal to 0. And, well, obviously, if it's equal to 0, then that means that it's equal now and we're at the equilibrium point. And if you recall, the equilibrium point, the pH there for strong acid and strong base reaction is equal to 7. So the answer to letter C is just pH 7. Alright, now, part D or letter D is different. However, it's also just really similar. Because now we've reached the equivalence point, right? So the more base we add, that means we're adding excess amounts of base. We no longer have enough acid to react with it, so the pH is just going to keep going up. Now, how do we solve for that? Well, knowing that we have excess titrant means that we have to adjust our computations to the fact that we're solving now for the concentration of the excess titrant. So our new equation would be the concentration of analyte is equal to, or rather, not the concentration of the analyte, the concentration of our titrant here would be equal to 0.125 times our new volume, 0.15 liters, minus our original volume. This is all over 0.3. Now, if we do this, we'll get an answer of, 0.125 times 0.15 minus 0.015. We'll get an answer of 0.00375 divided by 0.3. We have an answer of 0.0125 moles of NaOH. Now, how do we get the pH? Well, this time, since we have base, we'll actually be getting the pOH first. So that's negative log of 0.0125. This will get us an answer of, log 0.0125 not negative, rather 1.9. Now, how do we get the pH from this? Well, as we know, pH is just equal to 14 minus the pOH. So pH is equal to 14 minus 1.9, and that's going to be equal to 12.1. So 12.1 is going to be the pH once 15 liters of NaOH is added. So now we can plot our points. So here you can see that this is 0.1 liter. Right here, pH equals 7. And this is like 0.012 liters. And here, when we're like more than halfway through, somewhere around here, our pH is equal to 12.1. And this is at 0.3 liters. And that's it. That's how you plot the points of a titration curve. that's how you solve. So again, we have this formula here before the equivalence point, and we have this version, just the flip version, when we're past the equivalence point. So that's it. This is a supercut video of the pH, pOH, and titration curve concepts. So I'm gonna just end the frame here so that you guys can take a look at the titration curve. I hope you guys learned something, and I hope that yeah, I hope that this all makes sense, because titration is really crucial for higher level chemistry and even just in high school chemistry. You'll find a lot of interesting dynamics between acids and bases. You'll even be able to identify the interactions of some daily items that we use, such as vinegar and different bases, how acidic actually is our vinegar. So yeah, that's it, and I hope you guys learned something. Thank you everyone for watching, and I'll see you guys in the next video, whatever it may be about. Bye everyone.